All right, so what's the top right here? A 1, then what? 11, then what do you got? 121, what's next? 1, 3, 3, 1, next. 1, 4, 6, 4, 1. Good. Did you notice any patterns by any chance? We all start with 1 and with 1. Brennan, what do you see?
The one below adds up to is the sum of the two numbers above.
Bree, is that what you're going to say? So, Bree, if I asked you for the 5th row, what would you say?
I would say, 1, 5, 10, 10, 5, 1.
Yeah. Good. Yes, this is something called Pascal's triangle. Okay, that pattern continues over and over and over again. There's lots of other patterns going on. Some might have noticed the diagonals. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Those continue that direction. There's lots of exponent properties that have patterns happening in here as well. Once it gets bigger and bigger, you can see like so much more that's going on with it. It's pretty cool. The point of Pascal's triangle, okay, is to help us with some patterns that we can see when it comes to multiplying binomials. Okay, so if I said to do x plus 1 squared, did we already do this? You got x squared plus 2x plus 1, right? And then when you did x plus 1 to the power of 3, you got x3 plus 3x squared plus 3x plus 1. Do we see any pattern between what you got when you multiplied versus anything on the triangle? Would you say the coefficients here are 1, 2, 1? Would these coefficients be 1, 3, 3, 1? Yeah? Yeah, so the numbers from the row that matches the degree become coefficients. So the degree of a function equals the row in Pascal's triangle. Do you think that would continue if I moved on to x plus 1 to the power of 4? It does. So without having to do all the multiplying that you probably had to do for x plus 1 squared and x plus 1 to the power of 3, now instead of multiplying to itself 4 different times, you could say it's going to be 1x to the power of 4 plus 4x to the power of 3 plus, 6x squared plus 4x plus 1. Is there any other pattern you might have noticed when it comes to the exponents? Yeah, they decrease in order by 1. So the first exponent matches the degree of the function, and then it also decreases by 1 each time. Good. So this is simple Pascal's triangle. So 11, it just creates the pattern of the triangle. From here to build off of it, you would add. Like I know my next row is going to be 1, 6, 15, 20, 15, 6, 1. Like you would just build off of it using the previous row. But the pattern does come from powers of 11. Like that's how Pascal kind of started. Correct. Yep. Okay. So we're going to build off of this and we're going to do more with it later. We are going to do operations of polynomials today. So we're going to start off with adding and subtracting. And then we're going to build into multiplying. You've multiplied polynomials before. I know that. But you haven't done it to where it's like 3x plus 7y to the power of 4 to the power of 5, right? That's a lot of parentheses being multiplied together. Or we can use the binomial theorem and Pascal's triangle to set it up instead, okay? So that's like our grand finale. We will get back to this at the end. Okay? First, let's remember adding and subtracting, okay? Easy stuff. The set of integers is closed under addition and subtraction because every sum or difference results in an integer. To add or subtract polynomials, add or subtract the coefficients of like terms because adding or subtracting polynomials results in a polynomial, then the set of polynomials is also closed under addition and subtraction, okay? Very fancy for if you add and subtract a polynomial together, you get another polynomial. That's what it means to be closed under addition and subtraction, okay? You get the same type of answer as a result, okay? There's two different ways to do it. There is a vertical way to add and a horizontal way to add. Okay, I'm going to show you both. You pick which one you like and go with it. Okay, I like to give you options. The first one says to add 3x to the cubed plus 2x squared minus x minus 7 and x cubed minus 10x squared plus 8 in a vertical format. Okay, that means I'm going to stack them on top of each other. So I have 3x to the power of 3 plus 2x squared. I'm going to put a 1 in front of that x. Minus 7. I didn't change. There we go. And then vertically, so underneath it, I'm going to match my like terms. So I have 1x cubed. Then I have minus 10x squared. I don't have an x, so I'm going to put 0x in its spot. And then I have a plus 8. And it wants me to add these together. So this should look a whole lot like elimination. Thank you. Okay, same kind of format and style. We're just not trying to get rid of anything. We're just combining the two together. So 3x cubed and 1x cubed gives me 4x cubed. 2 minus 10 gives me negative 8. Bless you. Negative 1 plus 0 gives me, negative 1. I got this. There we go. Negative 7 plus 8 gives me a positive 1. And when we write our answer, we usually don't put that 1 in front of that x. Like that. All right, so there's the vertical way of doing it. We can also do horizontally, which some of you might be used to more. But some people, once they see the vertical format, they kind of like that better. So that's why I'm just exposing you to everything. So let's do two new ones, but we're going to do a horizontal format. Meaning we're going to have 9y to the power of 3 plus 2/3 y squared minus 2y plus 1. We're going to add negative 4/3 y squared plus 1y minus 4. From here, you would combine like terms. Start with our highest exponent. I see y to the power of 3. How many pieces have y to the power of 3? Just the one, right? 9y3. All right, how many pieces have y to the power of 2? There's 2 of them. I have 2/3 and I have negative 4/3. Well, that's nice. They have the same denominator. So I can do 2 minus 4, which gives me negative 2/3 y squared. And how many pieces have just a y? 2 of them. I have negative 2y, positive 1. So negative 2 plus 1 gives me negative 1y or negative y. Good. And then we have 1 plus negative 4, which is 1 minus 4, negative 3. Like that. Okay. Familiar? Yes? Okay. If I'm going too fast, let me know. We're going to do the same thing with subtraction then. Okay, so I'm going to show you the vertical way and I'll show you the horizontal way. Okay. When it comes to subtracting polynomials, what did you typically do before you actually subtracted? Yeah, you typically distributed your negative, right? And then it just became a plus problem again. Same thing's going on. I'm not reinventing the wheel here. We're going to do that same thing. We're just going to set it up to look a little bit differently than from what you're used to. And this is the algebra 2 part of it. So I have 2x to the power of 3 plus 6x squared minus 1x plus 1. And we're going to subtract. Oh, wait, I did it backwards, didn't I? Subtract that from that. Look at me, I fell for my own trick. We got to watch out with that wording, don't we? If I subtract 2 from 8, I'm doing 8 minus 2, right? Yeah. Yes, so I wrote the wrong one first. 8 needs to come first. Try this again. 8x to the power of 3 minus 3x squared minus 2x plus 9. There we go. Then 2x cubed plus 6x squared minus 1x plus 1. Okay, that's what we're doing. So again, watch for that word right there. Subtract this from that. We got to switch our order. So before I actually combine them, I am going to distribute that negative all the way through. So I'm going to make this second equation negative 2x thirds, negative 6x squared, positive 1x, and negative 1. Top equation, not going to change. And like elimination, I can combine them now with the signs that they currently have. So this becomes 8 minus 2. This is 6x to the power of 3. Negative 3 minus 6 gives me negative 9x squared. Negative 2 plus 1 gives me negative 1x. And then 9 minus 1 gives me 8. Come on. Skipping on me. Come on. So 6x cubed minus 9x squared minus x plus 8. Okay. So again, it's an old skill. It's just a new way of looking at it and organizing it. Well, it does not like the number 6. There we go. X. There we go. We got this. Whew. All right, let's do another one. Horizontal format. Again, recognizing that verbiage. We're subtracting 3 from 2. We're subtracting z from 3z, right? So we're going to do 2z squared plus 3z first. 2z squared plus 3z, subtract our other piece, which is going to be 3z squared plus 1z minus 4, like that. Just like before, let's go ahead and distribute that negative to all these pieces on this side. So we have 2z squared plus 3z, but now we have minus 3z squared, minus 1z, and positive 4. Just like above, we can combine like terms. 2z minus 3z gives me negative 1z. so negative z squared. 3z minus 1 gives me a positive 2. And then we had just a plus 4 on the end. Like that. Yes, no, maybe? Yes. So we remember it. It's familiar. It's probably not as straightforward as Algebra 1 might have looked. We got some fun terms going on. And I've given you a vertical and a horizontal way to do it. Okay? So if you've decided you like the horizontal better, then go with it. All right, ready to multiply? Refresh that skill. Yes, Miss Douglas. Woohoo! Okay, multiplying. To multiply two polynomials, multiply each term of the first polynomial by each term of the second polynomial. As with addition and subtraction, the set of polynomials is closed under multiplication, so they're closed under this as well. Okay? So when I tell you to multiply these two pieces together, you have options. Does it matter what order you put them in? No. When I go to do this, I don't want to put the trinomial first. I would want to put the binomial first. Okay? And I wouldn't be wrong doing that. So if I set it up, and I'm like, you know what? I want it to be x. Come on. Thank you. Minus 2.5 times negative x squared plus 2x plus 4. Okay? That's okay. If you didn't switch their order, that's okay. Order does not matter with multiplying. So what it said was to multiply each piece of the second polynomial with the first term and then the second term. So I'm going to distribute the x to all my pieces. So this gives me negative x to the power of 3. Remember law of exponents, we get to add. There's technically a power of 1 right here. Then we have plus 2x squared and plus 4x. Do it again, but now distribute with negative 2.5. Okay, so negative 2.5 times negative x squared gives me positive 2.5x squared. Negative 2.5 times 2x gives me negative 5x. Negative 2.5 times 4 gives me negative 10. And then we combine like terms. I see one piece with the x to the power of 3 at the beginning, right? And then I have 2x squared and 2.5x squared. So that gives me 4.5x squared. 4x minus 5 gives me negative 1x or negative x. And then finish it off with a negative 10. Do we remember? Am I going too fast? Y'all tell me, because I am kind of going quick. Okay. 2 people are feeling good about it. Okay, my next one, I have a binomial and trinomial again. I'll give you options. Did anybody, their teacher show them the box method by any chance of multiplying? Yes? Okay, so I'm going to show that also. So again, what I did for part A is horizontal multiplication. Okay, next I'm going to set it up like a times table. Okay. So I'm going to set it up. I'm going to have 3y squared minus 2y and 2. And then on the side, I'm going to have negative 1y and a positive 5. I'm going to build it like a multiplication table, like this. Okay. My visual learners typically like this better. So I'm going to multiply negative 1y with 3y squared. That gives me negative 3y to the power of 3. Remember, this has an exponent of a 1. Negative 1 and negative 2 gives me positive 2. Y and y gives me y squared. Negative 1 and 2 gives me negative 2, and I still have that y. And then across my bottom, we're going to multiply each piece by 5. So 5 times 3y squared gives me a positive, it's thinking, hold on, there we go. Positive 15y squared. 5 times negative 2y is negative 10y, bless you. And then 5 times 2 is positive 10. So notice when I did fill in my squares, I did include a positive or negative in front of them. Okay. So if you're used to doing it this way, what do we do next? Yeah, we find our like terms still within the table. Okay. My highest exponent is going to be y3. There's only one piece that has it, right? So negative 3y to the power of 3. Next, I see two pieces. Oops, that did not work. I didn't want to cross it out. I wanted to highlight it. There are two pieces with an exponent of 2. There we go. I have positive 2 and positive 15, which gives me what? Positive 17. Next, I have two pieces that have just a y. I have negative 2y and negative 10. So what's negative 2 minus 10? Negative 12. And then we have a plus 10 on the end. I don't like how that looks. I'm going to do it down here. There we go. That's easy to read. Okay. So that's like a box method way of setting up multiplication, which I typically use when I have when I have more pieces to multiply together. Like if I had a 4 times 4, I would definitely do this. I would not try to mess with horizontal distribution. All right. Man. Multiplying 3 pieces. Again, does order matter? No, it does not matter. So you're going to multiply 2 pieces together first, get that result, and then multiply it to the third piece. Okay? You can do a mix of horizontal distribution. Like you could do that first and then create a table afterwards. Whatever you want to do. I'm going to pause. You're going to try this one. Okay? Multiply these 3 binomials together. All right? Check your answers with mine. So I did a combination of the two so you could see it. I multiplied x minus 1 and x plus 4 together first to get x squared plus 3x minus 4. Then multiplying that with what's left over, the x plus 5. I showed that in a times table. And I got x cubed plus 8x squared plus 11x minus 20. Okay. Okay. You can't do all 3 at the same time. You have to pick 2 first. Get that result, and then bring in the third one. How we feel about add, subtract, multiplying? We good? Okay. Right? When it comes to multiplying, there are some tips, tricks, and shortcuts that happen along the way for us, and hopefully you will be able to recognize them. I'm going to remind you what they are, so you will recognize them when we see them in the future. Okay, you've done these before. There is the sum and difference. So if you're multiplying by a positive and negative of the exact same thing, it becomes a squared minus b squared. So example, like x plus 3 times x minus 3 gives me just x squared minus 9. That's the sum of difference backwards. I mean, the difference of squares backwards. Can't talk. Okay. We have shortcuts for the square of a binomial. So if we're adding or subtracting the same binomial to itself, multiplying it to itself, there's a pattern when it comes to its symbols. Same thing with cubes. If we're cubing a sum or difference of a binomial, there are some patterns that we can follow. Okay, so we're going to use these patterns to help us do the special products down here. Okay, so I have 4n plus 5 and I have 4n minus 5. Which special pattern does that follow, Zach? Yes, this is the sum and difference. Sum and difference. Which means I can set it up by doing a squared minus b squared. What's my a? 4. What's my b? 5. So be careful. This is 4n is technically your a. Minus 5. So your first piece is your a, your second piece is your b. So what is 4n squared? 16n squared. And then what's 5 squared? 25. So it becomes 16n squared minus 25, like that. All right, what special pattern is my middle one? A square binomial. Okay, so we're looking at that middle. It is a minus sign, correct? So we're going to do a squared minus 2ab plus b squared. My a is what? 1.4y is my a, and what's my b? My b is 2. Okay. So a squared is going to be 1.4y squared minus 2 times a times b plus b squared. A squared minus 2 ab plus b squared. That's what we're following from this one right here. Okay. What is 1.4 squared? Yeah, think of 14 squared, but move your decimal. So this becomes 1.996y squared. My middle, negative 2 times 1.4 times 2, negative 5.6y, and then 2 squared gives me 4. So we're doing this instead of writing it out, doing the distribution, adding like terms. Does that make sense? All right, and our last one, ab plus 4 to the power of 3. This is a cube of a binomial. So we're going to use, and it's a plus, so we're going to use this pattern right here. My a value is what? Technically a is ab, good, and my b is 4. All right, so a cubed is going to be ab cubed plus 3 times ab squared times 4 plus 3 times ab times 4 squared, and then plus 4 to the power of 3. So a product with an exponent, you know both pieces get it. So my first piece becomes a cubed b cubed. Our second piece, 3 times 4 is 12. And then a squared b squared. They both get the power of 2. Over here, this becomes 3 times what? 16. So that's going to give me a 48. A times b. And then we're going to end this with 64. Okay. Before we move on, stay with me. I'm going to show you something. What if I did... What if I pointed some things out over here? See how this was degree of 3? See how technically my coefficients were 1, 3, 3, 1? They were built in there. Yeah? Yes, no, maybe? Over here, power of 2. Notice technically my coefficients were 1, 2, 1. Yeah? So Pascal's triangle is still very much a part of when you are multiplying binomials. Okay? Hey, I am not packing up. I have 1 minute, don't I? Never mind. Dang it. Guess we're packing up. All right, we will do Pascal's triangle tomorrow. All right, and then we will start our online assignment, so make sure you have your Chromebooks, please. To be continued.